Hey, Vicky, are you there?
Hi, yeah, I'm here.
All right. Well, how's your day going for you?
It's been going well. How about yours?
Oh, it's going pretty well as well. It sounds like you're a little bit busy today.
Yeah,
How's the class coming along?
it's good. I still have some homework that I have to get done.
Okay, not a problem. I'm glad we can meet up here tonight and talk about some of these things with your math. Is the math class starting to get a little bit stressful or
A little bit.
a little bit? Well, hang in there. If you need any help, you're always welcome to reach out again. Let's just kind of jump into it because I know you're kind of on a clock here. You had some questions about the snowflake. Have you had a chance to look at this problem?
Yeah, a little.
Okay. What did you discover as you were going through it?
Uh, so I was reading the Wikipedia article on it,
Mhm.
and I found it interesting how the perimeter it went on for infinity.
I know it seems counterintuitive, doesn't it?
Yeah.
You would think that's going to be finite, but it's not. So it
Mhm.
tells you something about math. There's a lot of really crazy things out there. And whenever you start really dabbling with this idea of infinity, it's our intuition starts breaking down very quickly. And that's maybe because we have a finite brain, finite understanding of things. And if we try to comprehend the infinite, oh, we're in trouble. Now, can you see the bit paper okay?
Yes.
Okay. So it wants you to start off by looking at some equilateral triangle. And it's telling you that the distance here is going to be a value of 1. It really doesn't matter. Let's just say the initial value, here's our triangle. Instead of saying 1 foot, I'm just going to scale it. I'm going to say the perimeter. And that's how I'm going to designate the P naught. I'm just going to say L. So it might be 1 foot, it might be 2 foot, it might be 3 feet. I don't know. It's kind of an arbitrary measurement. Now, how do you make this triangle? How do you start it off?
Uh,
Well,
like
let's go to the next one then. How about P1? How do you do P1?
you add three more triangles into the middle of each line.
Mm-hmm. So you would take it and you would divide it up into 3 different pieces. You would put another equilateral triangle. And that's key. That's equilateral. That's going to be important. And my daughter might say it looks like a kitty cat. Okay. Then after you do this, if you want to get the next one, P2, what do?
You do the same thing, but on all of the sides.
That's right. So you do the same thing over here. You take this and chop it up into 3 pieces again, right?
Yeah.
Okay, so let's take a little closer look what we're doing along all these different line segments, because that's the key to the problem. If you take a line segment, length L. Now, again, it can be 2 foot, 3 foot. It doesn't really matter. We'll just call it length L. Then we're going to take this and we're going to chop it up to 3 equal pieces, like that. Now, since the total distance is a value of L, what's the distance for each one of these line segments?
One third of how.
Yeah, 1/3 of L. Okay, now what I'm going to do next is I'm going to take this and I'm going to take the line segment in between. And what I'm going to do is simply take it and kind of rotate it up. Now, again, what's the line segments length total here? It's going to be a third of an L.
All of
Yeah. And if I want to create a triangle, I'm missing something, missing a side. Put it in. Now, here's the key. It's equilateral, right? Since it's equilateral, it means all the sides are the same length. Here, here, and down there if I was going to have it. Now, that then tells us if I want to figure out the total length, if I was to be a little ant, get on here and start walking, I'm going to walk a distance of L over 3, come up this way, L over 3, come down this way, another L over 3, and then finally over here to another L over 3. So altogether, look how far we walked. Four-thirds L. Now, what that then tells us then is whenever we look at these line segments, as I go here to there, the new iteration, let's say if we went down this line segment, is that piece, which is 4/3. And then if I also note, I do the same thing right there. And I do the same thing right there, and right there, and right there, all the way around to create this new interesting fractal snow shape. Now, let me pause for a second, see if that's making sense to you right there.
Yeah, that makes sense.
Now, here's something else you can kind of think about where it doesn't make much sense at first when you start thinking it has an infinite arc length on a finite region. But each time, what you're going to be doing is just kind of popping a little bit more up each time. And as you keep popping it up each time, it's adding more and more to it. It's small and small, but it's going to be infinitesimally small, but you're going to keep doing it over and over and over. Now, what this tells us then, right here, is allows us to set up a recursive relationship. Remember we designated as P naught? That was the length of the whole entire triangle. And then as we keep creating our fractal, our interesting snowflake, I take the total length and I chop it up. Now, the thing is, I'm just going to do this in stages. I'll do it like stage 1, stage 2, stage 3. As I take this and chop it up over here, it's going to be a fourth or 4/3 of this length. Then 4/3 of this one, and then 4/3 of this one. And I can add them all together, or we also know since it's all going to be the same value, like we did over here, that just begs us to look at multiplication. So the next one here, it is going to be 4/3 of the previous length. But the next one is 4/3 of the previous length's previous length. Or in other words, when I get to P2, that's going to be 4/3 squared. Now, the recursive relationship, since you are talking about sequences and series, if I was going to write this in terms of recursion, I would say p sub n plus 1, 4/3, p sub n. And what kind of sequence is this called? It's not telescopic. What's it called?
A geometric sequence.
Geometric. Now, how do I know if a geometric sequence is actually going to converge? The thing that I'm powering up, it better be less than 1 in magnitude. So if I take X, and if I power it up, you only have 2 options here. The first option is this is going to go off to 0. Well, I guess really 4 options. We'll talk about 4 of them. The first option is this is going to go off to 0 if the magnitude of X is less than 1. In other words, X is between -1 and 1, not including the endpoints. If X is 1. If x is 1, you might get 1, but it does get a little bit fuzzy here because 1 to the 5th is, or 50th is 1. 1 to the 100th is 1. 1 to the infinity. Who knows what happens? You actually broke it here. And once again, this is where you have your finite understanding falls apart when you start looking at the infinite complexities associated with infinity. This is something that we study very intensely in calculus. This might be 1. It might be 3. Who knows? Time will tell. So, yes, use it with caution. If it's -1, this is going to oscillate back and forth, back and forth, back and forth. -1 to the 0th power, 1. -1 to the 1st power, -1. -1 squared, 1. -1 cubed, -1. So it goes back and forth, back and forth. And if x is bigger than 1 in magnitude, so bigger than 1, or you have it like this, watch out. This thing's about to explode. This is what we call diverging. So the only thing that really makes much sense here is if x, the piece that you're powering up, your common ratio, in other words, if that ratio value, if it's less than 1, it will converge. It converges to 0. But if that ratio, if it's bigger than 1, like we have in magnitude, this thing is going to do what we say, it grows without bounds. There's no stopping it. And that's where we get this thing going off towards positive infinity. Okay, now with all that said, we got the recursion, so we can grind these out really quickly now. But let me stop, see if that formula makes sense to you. Did you have any questions about how I went about finding it? And you can move the board down below if you like. Do you see the link?
I don't have.
You put it back in the chat box. Okay. There's a little palette down below, down here, and you can move it around. You can interact if you like. There's a 4-way cursor, so if you need to move to a certain spot, you can. There you go.
Yeah, like what did you mean by the on the right side with the geometric sequences?
The geometric sequence, what happens is if you're powering up the ratio, the common ratio, if it's way too big, this thing's going to take off like a rocket. It's going to go off towards maybe like towards positive infinity or whatnot. Let me show you a graph so you can better understand what's happening. Can you see the screen okay?
Yes.
And let's say if my common ratio is 2, and if I power it up, look what kind of graph I have. I have an exponential graph. And as terms get big, what happens to my graph? It gets pretty big, doesn't it? And even if I was looking at 1.5 and powering it up, it's still getting big, just not as fast. And if I looked at 1.00001 and power that up, look what's happening. It doesn't seem like much but I have to really zoom out. And then eventually, if I keep zooming out, I'll see that this thing's going to take off. Let me just take a few more zeros out and see if that's going to get us there a little faster. There we go. Okay, so that's what's happening with these graphs. They're exponential graphs. So if my base is bigger than 1, it might take a while, but see how it's eventually shooting up? Now, let's contrast that with, what if I went in a little bit closer, instead of looking at 1, looked at something like 0.5, and I raise that to the x power. Look what's happened to my graph now. It's dropping, isn't it? It's dropping fast. And if I looked at 0.01 raised to the x power, it's dropping even faster. So when I get to that value of 1, that's kind of like a fine line. I'm either going to go all the way up towards positive infinity or drop it down to 0. That's what that means over here with our common ratio.
Okay.
Good. Anything else on it?
No.
Good. All right. Now, does this formula make sense to you?
Yeah, I think so.
Okay. Let's just go through it one more time just to make sure so you can explain it. Start off with your triangle. And for each length here, we're going to subdivide into 3 different regions. Now, I don't want to look at it from down here. Why? It's getting convoluted. It's getting hard to see what's happening. So what I really want to do is zoom in and look at the line segment. No, I don't want to get trapped in the details and say the line segment's a third and it's going to be a 6 or anything like that. I just want to call it L, something that's going to be nice, reflective about what we're about to do. Chop it in 3 pieces. And just remember, it's like you're adding one more piece to it. It's going to be 4/3 of the previous value. And that's how we get the recursion, our geometric series or sequence. Now, with that said, let's calculate P2 and P1 and P3. Take it and plug it in. P1's 1. First answer is 4/3. P2. Take it in P0 again is 1. 16/9. P3. Do the same thing over and over. 4 to the 3rd power, 27 or 64/27. Here's our expression right there. So here's part 2. Here's part 3. Part 4. Just take what you have in part 3 and make it 20. Now, calculating this, good luck. It's going to blow your calculator up. Take your calculator real fast and try it. What's 4 to the 20th power? Did you get anything useful there?
I got 315.
Is there an E at the end?
No.
Let me show what you would get. If you were to take it 4 to the 20th power, that's your value. Now, if you take 4/3 to the 20th power, that was a little bit more manageable. But eventually, it is going to get out of control. This is what I get for the 20th power. So after doing this 20 times, 20 iterations, it's like I took a length of 1 foot and it really got that going exponentially, that is. Now, number 5, that's a fantastic question. I'm loving that question. What's the smallest value you can get to the moon and back? You don't want to stay there, do you? How far is it to the moon? Let's find out. So the moon, Earth, and let's go to NASA's website. The moon is an average of 238,855 miles. Talk about a road trip. Okay, there we go. Now, here's a question. When I'm doing this fractal, what was my original units?
It's in feet.
What measurement did I just give you?
Miles.
So we got to do a little conversion. How do I convert this over from miles into feet? How many miles are in a feet? And how many feet are in a mile?
Mm.
5,280 feet. Okay, so there's my conversion factor. How do I express this into terms of miles? You want to hear the secret behind doing it? Shh, don't tell people. Follow the units. What units do I have here?
Miles.
What units do I wish I had there?
Feet.
Look at a conversion factor over here. For a conversion factor, we know this. For every 1 mile equals 5,280 feet. And when I say follow units, what I mean by this, what if I was going to cross them out now? Like, cancel them out. What's my units that remain? Feet. So if I follow the units like this, set up my ratio, my conversion factor, you're going to get the answer that way. Okay, let's just calculate this and see what we're going to get. And that's what I get. It's a lot of feet, isn't it?
Yeah.
So, what's the smallest n could be that we're going to get to the distance to the moon? This right here is the distance from the moon from the Earth in terms of feet. I want to go that far. Now, what this is talking about when it says the word smallest, what comes to your mind when you hear the word smallest or largest? What kind of math operator? Is it equality? Not necessarily. So I might want to look at something like less than or equal to or greater than or equal to, however set this up. So I just want to make sure that I get the bare minimum that I'm going to need in order to get to the moon. See if that makes sense to you.
Wait, why is it greater or equal to?
Well, we know we can actually we can overshoot it, but if I want to make sure that I actually do hit it without overshooting it at all, here's what we can definitely do an equality if you wanted to. I just got to be a little bit careful about maybe how I proceed. If I say this, I might overshoot it a little bit, but I can always take the absolute value. I can floor it if I need to, round it down.
Okay.
All right. Now we got our value. We got our formula. Remember P naught? What was that value again?
Wait, what
was P naught again?
1?
Let's plug it in. Can you solve for n? If you can solve it, you got it. How do you solve this? Use logarithms. What property of logarithms can help me out here? Is it the addition property? Subtraction property?
I forget.
The exponential property. Because what if I took the natural log of both sides? Or what I do next? Right in front. Then how do I solve from here? How do you always solve? If I gave you 5x equals 6, how would you solve for x?
Divide.
So how would you solve for here then? Because that's just a number.
You also put it at the bottom.
That's right. Divide it. Now, let's take a look at this and let's see what we're going to get. All right, so here's what I get for n. 64839. Okay. Does that make sense to you so far?
Mostly.
Okay. See, go ahead and rewind it a bit if you need to. Make sure you get it all. Is there a part up here you're not sure about?
Yeah, I forgot a lot about logarithms since I learned them last year, and so they're still confusing to me.
Not a problem. Let me send you a link here. This is going to help you speed that up a bit. So over here, what I have for all my students is they have access to the website. So you have access to using all these properties of exponentials. And look down here, Vicky, look at this. All your different logarithm properties you need to know. So I'll drop this over in the chat box for you. There you go. And you can bookmark this website and come back to it whenever you need to.
Okay, thank you.
Okay. Now, let's go back to this one. We got n equals 34.839 using properties of logarithms, solving. We got a little problem. See if you can find the problem. What do all these values have in common?
A whole number.
They're all integers, aren't they? Is this an integer?
No.
No, it's not. So the answer is not 64.83. I'm looking at n as being an integer. And that's something they're probably going to be looking for to see what you're going to do about it. Now, again, in order to get to the moon, it's 64.839, but n's not in decimal. It's an integer. So what I need to do is I need to take this, round it up to make sure I get there. If I round it down, I almost get there, but not quite. If I round it up, I do get to the moon. I just overshoot a little bit. That's okay. I just back up and hit the reverse if I need to, get back to where I need to go. So n is an integer, and that's kind of the trick here. And if I want to get to there, 64 is not good enough. If it was 64.3, it's still not good enough to say 64 because I'm still a little shy. If I want to make sure I get to the moon, pack a little bit more. In other words, you round up. 65. Now, that's where the inequality came into play. P sub n is greater than or equal to whatever that value was over here on the right-hand side. And what you would need is you would solve it for an integer. Now, if you don't work with the inequality, that's okay. You can work with the equality, just make sure you round up when you get done. Good. Look, it's a great problem. I'm loving this problem. Is there anything else on here you're not for sure about?
Just like, well, when it says the common ratio, what exactly does that mean?
That's the 4/3. Back over here. It's whatever you're powering up. That's the common ratio.
Okay.
So R is going to be 4/3. Now, another way of how you could solve this is you could just simply look at the iterations 1, 2, 3, 4, and then you can take P1 divided by P2. And or you can take P2 divided by P1. Let's do it like that instead. You get 4/3, and that's your common ratio. That tells you how things are growing. As you go from one iteration to the next, it grows by 4/3 to the previous value. Good.
Okay. Yeah.
Okay, what else do you have? Did you have another question about these 5?
But for the final answer for PN, I got 72.8 when I put it in my calculator.
Calculator might have broke a little bit. Let's just do it here again together, though. Okay, can you see the screen okay?
Yeah.
All right, so let's see our equation again. Is we have 4/3. Raise that to the nth power. And this calculator, this is a real powerful calculator. It can handle it. So we're going to have 1261154 Let's actually solve it. And I get something really interesting. Let's do that again. Let's switch up and say X just in case. No. Oh, it's doing some things that you're not ready for yet in your class. That's why it's saying this. That's what I want right there. And you're right. I am getting 72. So that's going to be rounded up to 73.
Okay.
Yep. 73 then. Good. Anything else here?
Stop running, bro.
Can we go back to the page?
Oh, I see my error. A little hard to see. I forgot my extra one. That's where it was. Okay, back to the page. All right, can you see it okay?
Yeah.
Okay.
Those are all of my questions.
Good, good. Okay, I was looking at these over here also. You want to talk about these two?
Yeah.
Perfect. Talk to me about number 14.
So we're doing probability, and this is one of the questions in we have the high mathematics workbook.
Mhm.
And
What's probability?
the chance that of something to occur.
Okay. How do you calculate it?
You do the chance that of the outcome that you want versus the over the total possible outcomes.
Right. Now, I probably wouldn't use the word chance because that kind of does conjure up a little bit sometimes of a different idea. You start talking about odds for and odds against, and that's a little bit of a different calculation. Probably the better way of thinking about this is this: part over the whole. Okay. And probability, well, could I have 110% probability?
No.
No. We say it sometimes. It just means that we're really, really certain about something, but that's not really true. It's always bigger than 0 or equal 0 and no bigger than 1 or it could equal 1, 100%. Okay. So if I'm looking at a deck of cards and 2 cards, if I was going to draw them, if 2 cards are red, what's the probability that this is going to happen?
To
How many red cards are there in the deck of cards?
26.
Right. 26 red and 26 black. So I'm going to pick 4 cards. And when I pick the 4 cards, no replacements. I'm not going to take a card and put it back inside the deck. I'm going to take it and lay it on the table. Now, when I go about this, there's 52 cards. What's the probability that the first card is going to be red?
1/2.
Okay, you can think of it as 1/2, but let's think about it in a little bit different limelight. Part over the whole. There's 26 cards to choose from at 52. Now, looking at it from this vantage point really helps us then to decide or to see. The next one is part, because there's 25 cards now, because one of the red ones is gone. There's only 51 left. And then for the next one, just remember again, part over the whole. Makes it so much easier. Look at these problems you do that. There's now 50 cards, but there's 26 black ones. There's 49 cards to choose from. Then there's 25 black ones to choose from. Now, because really all these events are pretty much like mutually independent, after I take one off the deck, I can shuffle it again if I need to or if I want to. And the next card that I pick, after it's gone, the first card has really no bearing on what's going to happen thereafter. So I have the multiplication principle in play. That's my probability. Now, I could have picked the black card first, but if I did, that really wouldn't matter much because I would just take this and I would just commute it, the values around. Okay, see if that makes sense to you.
Okay, that makes sense.
Perfect. What about the next one there? At least one black card is drawn. Oh, what does that mean to say at least one?
There could be one or more than one.
That's right. Well, I can do one card or two cards or three cards, four cards. But that does add a layer of complexity to it. I can look at the probability that I have one black card. So one black and three red. Then I can look at the probability of having two black cards and two reds. Or the probability of having three black, one red. Or the probability of four black and zero red. Now, I either have a handful of cards which have one black, or I have a card with two blacks. I can't have a deck of cards which has both two black cards and one black card at the same time. It's either one black card or two black cards. I can't have both of those situations. So that tells us then it's mutually independent. What I do from one to the next, to the next, to the next. Instead of looking at least, I can look at this in terms of I want to add everything together. But I do have the other case. What about the other case back there? The probability of no blacks and four reds. Now, Vicky, what does this all say? When I look at the events, I have the event of I can look at no black cards, one black card, 2, 3, and 4. If I add this up, what's my probability?
So if you add them all, it'd be 1.
It would be. Why is it 1?
Because those are all the possible outcomes.
That's right. Think of it like this. You either do it or you don't. Well, if you either do something or you don't do something, what's the probability of that happening? It's 100%. So either you do event E or you don't. It's 100%. Now, you could work this problem and sum everything up. That takes a long time. See, it's a whole lot easier if you just take this, move it to the other side, and say 1 minus the probability of no blacks. Then I get the probability of at least 1. So if I have a deck of cards, clear deck of cards, what's the probability of having no blacks? I'm going to draw 4 cards. They're all red. $26 to start off with, then 25, then 24, then 23 left. At least one black picking. See if that makes sense to you.
Yeah, it makes sense.
Good. Now, let me get these out real fast. First one, I have a little bit of a round off. It's actually going to be this. And for the next one, I get that. How you feeling about it so far?
Good.
You ready to hit the next one?
Yeah.
And let's do it. Oh my. What's happening here?
Yeah, I was just confused how to like find the probability was the diagram on the right.
Okay. Tell me what the diagram's doing. What is that trying to tell us there?
The different switches.
Okay. And if I'm going to electrify it, if I'm going from A to B, what do I need to happen? I need one path. So I want to go something like this. Now, what does P represent?
And the probability that they're closed.
Okay. Right now they're open. I need them closed. I need to create that circuit. Now, in order to go from A to B, let's take a look and see what we need to happen. So here's what I can do. I can look at different possibilities here, different scenarios. I could go from A up this way and down that way. And then we got it. I can go down this way and then we got it. Now, it's possible that this gate right here can be closed and that can be closed, but the other ones are open. Do I got it?
No.
No, I don't. So the first thing that I want to do here is I just want to pause for a second and make sure that I understand what this problem is telling me. It can be a little confusing at times, for sure. Now, after we got a good understanding of what this is telling us, we make the observation that there's really 4 outcomes I need really to consider. Because this can be closed and that can be closed, but the other ones can be open. Or this can be open, these can be closed, but I'm still not getting through. So let's go ahead and label this. Just gives our little bit of bearings. Let's call this A, B, C, and D. What's the probability that A is closed?
Mm. 1/2.
Not 1/2. All 4 switches operate independently. The probability of each one being closed is P. What's the probability of, just looking at this one, if I was to take it and close it?
Is P.
It's P also. Good. Now, if I'm going from A to B, I need to make sure that these things are closed. In other words, what's the probability of A and B, of these 2 events happening? Put in set notation, let's say it like this. Probability of A and B. Look right here. They're independent. Multiplication rules in play. Since they are independent, we know this. Multiplication rule of independent events. And you just told me that P and P, that's P squared. Now, what do you think is going to happen down here? Same thing, right? Okay, does that all make sense?
Yeah.
Now, let's get a little bit more probability-ish about it, if that's such a word. We'll say event 1, event 2. So if I want to complete the cycle, the circuit, should I have the first one or the second one? Or does it matter?
Does it matter?
That's right. So as long as I have E1 or E2. But wait a second. Haven't we seen a spoiler before? The law of inclusion and exclusion? Absolutely. So what's the probability of event 1 happening?
T squared.
Probably event 2 happening.
P squared.
And probably event E1 and E2, that means everything's closed. What's that probability of happening? Close them all. If I close them all, what's that probability?
Two P.
Probably for each one closing is what? P. Probably the next one closes is P. Probably the next one closes is P. And this one is P. They're all independent. p to the fourth. So here's our probability. Wow. See if that makes sense to you.
Okay, yeah, it makes sense.
It takes a little while, but once you see it, you're like, wow, of course. This is amazing. We just found A. In terms of P. 2p squared minus p fourth. Find the least value, which probably is going to be more than 0.5. Okay, let's do that. Let's just say equal. It is an inequality, but we'll find that boundary. Okay, no, it's 0.5. We can make it a half. Yeah, let's just throw it to the other side. Everything. And we get this. What kind of equation do I have? It's a degree 4. But it is a trinomial. And this is really interesting. What if I just turn my head for a second, squint an eye, and look at it from the other's perspective? What kind of equation do I have now? That's a quadratic. You think you might be able to solve the quadratic equation?
Yeah.
How would you do it?
I need to assign like A, B, and C. So it'd be 1
Yeah, go ahead.
and then -2 and 1/2.
Mm-hmm. Now, as we solve it, after we use a quadratic formula, we get these crazy answers. Wow. It's crazy. Now, I'm solving for not you, but for P, remember? So I got to come over here and replace them now with P squared. That's the next piece of this puzzle. After you solve them, back substitute it. Now, once you've done that, take the square root. And you do want to look at plus or minus, but since we're looking at probability, it's not going to make much sense like a negative probability. So we'll just take the principal square root. And here's our principal square roots. The question is, which one do I take? Because what did the problem state? Let's go back to it. Find the least value for P. P's probability. Probably is between 0 and 1. So when I look at these values a little bit closer, I realize this is actually 1.30. This one, 0.54. This is my p-value I want. And that's the exact answer. All right. All right, Vicki, how you feeling about it?
Good.
Better. The hard part in this problem was making that observation that, okay, everything's got to be closed. Okay, what's the probability of that? Well, that's P. And then making the observation down here that you're looking at this law of inclusion and exclusion. This formula is really important. Make sure you remember this formula. That comes up quite a bit in probability. You're going to see it again and again and again. And then the next piece of the hard part of this puzzle was find the quadratic structure and jumping on it. So if you see three terms like we saw right here, think of maybe quadratic formula because it might be the ticket. Now, it may not be, but it might be. If I had something like p to the 6, p cubed, I'm going to use the quadratic formula, but I'm going to set equal to p to the cube to first reveal that structure. Then I'll use the formula. Good. Well, Vicki, take a look at the rest of your problem. See if there's anything else you want to talk about.
No, that was all.
All right. You feeling pretty good for the evening?
Yeah, thank you.
All right. So hopefully it gets you a good running start into the week as you're getting ready for your other classes.
Yes.
All right. Well, if you need any more help, just let me know. I'll be glad to help you.
Okay, thank you.
All right. Take care.
Bye.
Bye.
I hope that today's lesson was a positive and an encouraging learning experience, and that you have a better understanding of how to solve these problems. Be sure to set some time there today and throughout the week to review these concepts, to rework these examples so that you're better prepared for the next lesson. If you need anything, just let me know. You're always welcome to send me an email or to stop by during office hours. Until next time, keep up the good work and have a great day.